So I've never had the good fortune of meeting Bohm and not yet Susskind, but I was extremely fortunate to have Yakir as my PhD advisor together with Benny Resnick. And if I have to tell you in one minute what it's like...
No, microphone. That's the microphone for the posterity.
Oh, sorry. Off. Is it okay now? So if I want to tell you in 1 minute what it's like participating in the research group of Yakir, I would say the word that sums it best is ongoing workshop. He was always there with his trademark pipe or sometimes a cigar and always working on some new ideas. And people constantly coming in, taking part, leaving, and just nonstop research. And of course, the preferred mode of operation is paradox. So for many years, Yakir's trademark course, very popular course at Tel Aviv, was quantum paradoxes, and now we can all enjoy it through this book that has just been advertised several times together with Daniel Rohrlich. And they give this motto from Wheeler, no progress without paradox. So I think that pretty much summarizes the motto of the group. So I'll do my best to present this as a paradox or apparent paradox between some work that Yakir did with Lenny Susskind many years ago, where they considered the possibility of having superpositions of states with different charges, among other things. And can this, and showed that apparently, at first sight at least, it seems to enable us to violate the non-locality of the AB phase. So again, just a quick reminder, we know that the AB phase can be measured for a closed trajectory for a loop, but it doesn't really make sense. We can write it down, but it's gauge dependent and shouldn't be measurable for an open loop. And I will try and see how this is not violated or is violated when we consider these exotic states. So this brings us to the question, the basic question behind the AS paper papers was, are any quantum superpositions possible, at least in non-relativistic quantum mechanics? So let's just begin with a quick review of quantum superpositions. So the simplest one.
What is PNN?
Sorry, I will go back to this, of course, but this is supposed to be here a proton and a neutron, and we have the superposition of having either one or the other, but not just as a classical probability, but actually in a quantum superposition. So what is a quantum superposition? The simplest one, intuitively, to my mind, is a superposition of polarization states for a photon. So here we have equal amplitude to be in vertical polarization or horizontal polarization for a single photon. But there are many different ways of doing this. These are 4 different states that all have 50-50. If I just measure for these 2 polarizations with some polarizing beam splitter, they're all equivalent. They're all 50-50. And that's just classical probability. But in quantum mechanics, we also can put a phase in front here. And in this particular case, there's this very suggestive notation tells us that they have very simple visualizable interpretations, these different states, different kinds of polarization. They have classical analogs. And basically, I can distinguish them the same way I distinguish the analogous classical states. So here it's reasonable. Even classicists don't have a lot of problem with this. How about what would be more radical? Having, say, an atom in a superposition of 2 energy states. Now, of course, I can have a probabilistic, classical probability to find it in one or the other, but in quantum mechanics, we say it can really be in both at the same time in some sense. What sense? You can actually put a phase in between and measure it. It wouldn't make sense if I only have one or the other. And this is a schematic of some apparatus that is actually used to prepare and measure such phases, and I'll come back to it in two slides. It's called a Ramsey interferometer, and it's of great practical importance because it's a component in atomic clocks and other very important applications. Okay, so how about superpositions of charge states? Well, up until 1952, since for about 20 years, since von Neumann's formalization of quantum mechanics, just about any superposition you could write made sense, and should have been physically meaningful. But in '52, Wick, Whiteman, and Wigner, WWW, the original WWW, introduced the very important concept of superselection, which means not everything you can write down is really meaningful. You can write two different superpositions of with different phases in between. We know that a global phase doesn't carry any information in quantum mechanics. They said if you have two states with different charges, then this is a generalization of the fact that both of these should be treated like global phases. So you can't tell the difference, even though there's a different relative phase here and here. They're really the same classical probability distribution. The phase is not measurable in any possible way. So for another 15 years, that was you couldn't measure it, not even conceptually. And then two young professors at Yeshiva took a deep look at this paper and realized that if you take the logical conclusion to its bitter end, then you could actually set up paradoxes with your bread and butter variables that x or p or L, and you could show that in some situations you shouldn't even be able to measure those, and that really didn't make any sense. And to resolve this, they introduced the concept of frames of reference within quantum mechanics. And this is a very deep paper or set of papers, but the upshot is it does make sense. If you're careful enough in your interpretation, it does make sense, and conceptually you can measure this. So is it just conceptual, or do they have an idea how you might be able to do it? Well, at least in a Gedanken way, they gave it away, which is really, I mentioned this Ramsey interferometer. It's an analog, and a very exotic analog of such a Ramsey interferometer. But so I'll say a few words about this. In this device, you put in an atom in its, say, ground state, goes through a light field, a cavity with a coherent state of light, interacts. This light field has a well-defined phase. It prepares it in a superposition, and if you can use a second such coherent state to measure this phase. So if we have Alice here preparing, or more appropriately, Aharonov preparing the states here, and he doesn't tell Bohm what the phi he chose was, but he sends him a bunch of these. By an independent measurement here, he can determine this phi, just by physical measurements. Now, to convert this into an AS scheme, you have to replace the photons by some charged mesons, pi minuses or something, and a coherent field, and the whole thing goes through. You replace the ground. So proton is converted into a superposition of proton and neutron, and you can measure the phase. Okay, so where's the paradox? The tension comes in here. So what happens if I drag a particle initially? If I just take a charged particle, the Aharonov-Bohm phase is an overall global phase as far as it's concerned, if I have nothing else. But if I have this superposition, let's say the neutron here is chargeless, I'm ignoring spin, it just doesn't accrue any phase. But the proton is charged, and it does accrue. So now, after dragging it carefully from A to B, this Aharonov-Bohm phase is an internal phase, a relative phase within the state of this particle. And W3 would have said that this is the same status as a global phase, and it's just unphysical and ignore it. But I've just argued that you should that they are actually physically measurable, both phi A and phi B. And this all you have to do is some arithmetic, and you get them. The difference should give you the Aharonov-Bohm phase without non-topological phase. So something must be inconsistent. Either one of the assumptions is wrong, or somehow the reasoning is faulty. Is it the non-locality of the Aharonov-Bohm effect? Is it the locality of the AS, the ability to measure an AS phase? Does this thing pick out a particular gauge, break gauge invariance? What is something has to give. So I'll give you a second to think about it. Yeah.
I think I know where you're going, but
Yeah.
you can't just, given a state, you can't measure the relative phase.
Which I'm talking about the relative phase between the N and P here.
Right.
It's like the phase in a coherent state. It's a relative phase.
Given one sample, this is
Well, suppose I send 10 of these. That's not, when I say one particle, I mean that I don't have a pair between two particles, but I can send many copies and do a complete tomography of this state. Given this exotic Ramsey.
But you don't need real protons and neutrons.
Well, it's a Gedanken thing, of course. There are a million reasons why this would be complicated in practice. But even conceptually, this shouldn't make sense a la Wigner.
Spin up and down in either.
Yeah.
Same way.
So is it really an inconsistency or just a storm in a teapot? Well, so the resolution, there are various ways of looking at it, but basically it's a question of calibrating. We're comparing things happening at two different points here. So when I'm comparing the phase at phi A with the phase phi B, I said there is some concept of, which I didn't go into, of these quantum state frames of reference. We're comparing frames of reference defined at two different locations. So how do I really calibrate them? Is there too much freedom here? Is there an unambiguous way of comparing phases?
Suppose you have a
Yeah.
closure, even there, you still have one will pick a phase and one will not. So,
Yeah.
and this.
No, it's okay that they do. The problem is not that this doesn't pick and this picks up a phase, but that now it's within the same. Locally, I can see this phase. I claimed I can measure this phase between them.
it's not a gauge invariant statement.
Okay.
Yeah, I'm violating gauge invariance. And,
You don't want to.
yeah. So there are various different ways of looking at it, but I think the most naive way is just to ask, okay, how do we compare? How would you compare this? Take two coherent states, identical coherent states prepared at A. You can compare them. And leave one there to be used to measure phi A. Take the other one along some trajectory, C prime or C double prime to B, and use it to measure the phase there. So what happens? You pick up it turns out you do the math, and you're still in a coherent state, but you pick up a phase, and this phase is exactly the phase up to sign that an electron would get the AB phase in the same gauge that you would pick up, that an electron would pick up. And when you use it to measure the state of this relative phase, you're really looking at the difference. So if I calibrated my coherent state at B using C prime trajectory, the difference would just be 0, and my observer would say that no relative phase was picked up. The same one. It still has the same one it had at A. And at C prime, it would actually, double prime, it would actually be a little different. It would actually, they together complete this loop. And it turns out they would just pick up the full topological AB phase. And basically, that's all you can have, either 0 or some integer multiple of the topological phase. So this is really not, I cannot get from this the AB part of or this C part of the total loop. What I do get here is a two-particle, really I should say two-body Aharonov-Bohm effect, where two bodies together complete the loop instead of one. So in summary, we just got that this local relative phase measurement gives us just another variant of the two-body AB effect. I don't say two-particle because the coherent state is a many-particle state. So we can measure the relative phase between charged states. At least I didn't prove it here, but it's still consistent. It's physical, but it makes sense at a point. Comparing the two relative states at two different locations is not an unambiguous thing. I have some freedom, so I can't use it to set up a paradox. So thank you.
Thank you very much. having time for one question because we started 2 minutes
late.
Question, yes. Oh, no, 2 questions. Okay, very good.
Yeah.
Eduard, please.
So you consider proton plus neutrons,
Yes.
but you can probably consider electron plus positron.
Yes.
Or for solid state physics, electron plus four.
Consider mass.
Yes, yes, yes.
So
Electron
can you
plus
have implication for this because you have electron? Maybe your effect has implication.
The
Some
kind of
application
yeah.
of solid state physics.
Electron and neutrino would be
electron and a hole.
Actually, recently, some Dowling et al. Had a paper about a superposition a proposal for an experiment with a superposition of an atom and a molecule. So you can violate very crazy things in this same spirit. But yeah, yeah. Well, this is a very Gedunken thing, of course. There are good reasons why it would be extremely hard to do this, but maybe one comment is that it's of great practical interest, not because of the esoteric charge states, but actually it's come full circle now. And for the humble photonic coherent state, people have said there's actually an almost superselection rule in the way you produce those with a laser. And how can you really talk in that language in the regular Ramsey, which works like a clock, the best clock we have? And they actually went back to this paper after 40 or 40-something years to understand what's going on there.
You know, this is Aharonov-Bohm loop, starting from Pauli and coming back to Pauli. Pauli discovered the young news fields, you know that. Right? I mean, the letter to Pais.
Yeah.
Just one small comment. Question.
Yeah.
That was order. Left, that was another question.
Just
Yeah.
the point here is that you use a coherent state of piles. Therefore, neutron plus essentially you so neutron and proton is fine, but you cannot have coherent state of fermions. So not everything is meant.
Okay, you could even say that's even worse. How can I, if I just wanted to prove fermion and boson, you're saying won't work, or what? I didn't understand.
You can measure relative phase between vacuum and one charged boson. You cannot measure relative phase between vacuum and an electron.
I thought you were going to say something else, and I'm really begging the question. But okay, I won't ask myself a question.
If we are continuing this, I would say maybe after if you finish this talk, we'll. You have a remark.
No. It's not so.
Okay.
But I would responsible to finish this on time.
Okay.
Professor Gitman, thank you. Let's thank the speaker again.